pieces that you've been working on. The composite argument properties, which, if you've been paying attention, every other property that we've done since that has been built on the composite argument property. The composite argument property is basically like the foundational property, and then all the other ones are manipulations of that. So like cosine 2x, you could write that as a composite argument by writing it as cosine of x plus x, and then use the composite argument property to write it in terms of sines and cosines. You did that on the sheet. And then by performing algebraic operations on the double argument properties, we can derive similar half argument properties. So double arguments and half arguments. Let's just talk about that real quick up here at the top. If I have cosine of 6x and cosine of 3x, is one double the other?
Yeah.
So could I write cosine 6x as cosine of 2 times 3x? Is that essentially the same thing? Okay. A double argument doesn't necessarily mean that your argument will always be written with a 2 times something. It might be that the number is just double of whatever that is, and then you would have to rewrite it. But can I rewrite that always with a 2 times something else to show that it's double of the other? Like if I had cosine 4x, what's cosine 4x double of? Like what? 2x. And I could write cosine 4x as 2 times 2x, right? So that we can use the double argument property. Because sometimes when you're asked to use the double argument property, it's not written as a double argument. You have to rewrite the argument so it looks like double of something or 2 times something else. Half argument, same thing. That's just reversing the process where now cosine 3x is half of the other argument. So I could write 3x as cosine of 1/2 of 6x, essentially. So it's connecting. If you have two different trig functions, it's looking at their arguments in terms of double or half of the other. And then that allows you to use those properties for half arguments and double arguments.
Is this only for cosine?
No, any. Well, cosine and sine are the only ones. Well, no, tangent we also deal with. But we don't do anything like secant, cosecant, cotangent.
So we're done with cosecant?
I'm not done with it, but in terms of the properties, we just deal with the main ones: sine, cosine, tangent. So in this section, we're going to learn these properties, or at least use them, and show that the product of two sinusoids is a sinusoid with half the period and half the amplitude, which we've already done a little bit of work with, but this is just digging a little bit deeper. All right, so for this one, the figure above shows the graph of y equals sine x cosine x. It appears as the sinusoid with half the period and half the amplitude of the parent sine and cosine. So if you can delineate between the two, this is my regular cosine function that you see, the like many dashed graph. The spread out dashed graph is the regular sine, and you can see when you multiply them, it becomes shorter, squished a little bit, so it looks like it has half the amplitude of either one of them. And that it's squished this way, so more cycles are happening in one cycle of the other. So you can kind of see that both sides kind of squish together. The equation of this graph, this solid graph here, is 1/2 sine 2x. And the work below would show that it's true. So we're going to take 1/2 sine 2x. Using a property we've already proven to be true, I can rewrite sine 2x as sine of what? X plus x. I can write it as half of 4x, but we haven't proved that those are true yet. So we have to use something we've already proved is true. That's the composite argument property. So I can break that up. Actually, I'm going to do it that way. Sine of x plus x, or sine of a plus b, is sine of x cosine x. And is it plus or minus? It's plus. And then it's cosine x sine x. Now, I know it's a little confusing because both arguments end up being the same, but you would switch it if it was like two different things.
Well, it also makes sense because x plus x are the same. So.
Right. So then these are essentially the same, right? Sine x, cosine x, cosine x, sine x.
Yep.
Are they the same term? So I could add those together to get 2.
Yep.
And by adding them together to get 2, what happens with the 1/2?
Becomes
Becomes
1 when it multiplies.
1 when you multiply and just gives you sine x cosine x. So it's the proof, the algebraic proof, that this expression is the same thing as multiplying sine x and cosine x together. You end up getting the same exact graph, but proving it using some properties that we've already proven are true. So that is one property that we'll see a connection with here soon. On the next page, you're going to see two graphs, the square of cosine and the square of sine. Both cosine squared and sine squared are sinusoids with amplitude 1/2, period pi, and a sinusoidal axis of y equals 1/2. And then notice that they're a half cycle out of phase. So we've kind of talked about this already, where you have cosine squared, that's the dashed graph, and then whenever you square something, like if you have a negative number and you square it, what happens? It's positive. So if you kind of look at this graph here, doesn't it look like the negative part of the graph flipped up above the x-axis? Yeah, because it's kind of like making an absolute value, making all of your negative values positive. Didn't that same thing kind of happen here with the sign?
Yeah.
Yes, the negative part flipped up above. Yes, sir.
Doesn't that change the sinusoidal axis though?
It is, yep. So on the previous page it was saying that sine squared and cosine squared, it's going to actually, the new graph looks like it's half the size, because now the sinusoidal axis is at 1/2. So it looks like the amplitude got squished. And doesn't it look like your period got squished, too? Just like on the other page? Okay. This is why, though, when you add sine squared and cosine squared together, you get 1. And we kind of talked about that before, because wherever, like if this graph was here, did I draw that right? I did. If this graph was transposed onto this one, and you were to take the y values at any point and add them together, like the easiest places to see would be like high points and low points here. This y value is 0, this y value is 1, so 0 plus 1 would give me 1. And then if you were to take this y value and this y value and add them together, you would get 1. So no matter where you're at, those y values that line up would always equal 1. That's why sine squared plus cosine squared equals 1, graphically. Alright, so underneath here, products and squares of cosine and sine. There's some properties that might come up. We have to use them. So sine x, cosine x. This is like the first two graphs that we looked at on the front page. You can rewrite that as just a sine with a double argument. And we proved algebraically why that was true. We can also write cosine squared x not only as 1 minus sine squared, but because it looks like it's half the amplitude and half and the sinusoidal axis is 1/2, you can rewrite that as 1/2 plus 1/2 cosine 2x. So not only is cosine squared equal to 1 minus sine squared, but now it's also equal to this, which sometimes might be more useful than the other. And then sine squared is essentially the same thing, but if you look at, that's cosine. If you look at sine squared, the solid graph here, essentially it starts at a low point. So actually sine squared can be rewritten in terms of cosine this way. So these are just properties, these are on your sheet. So if we come across a time when it would be useful for us to use them, this is kind of the little proof that we've done so that we can use them. The ones that are more common are the double argument properties, and we're going to prove a couple of them here, and you've kind of actually already done this on your own, but we're going to get it in your notes here. DAP, double argument property for cosine. These are the more common ones, more common than these, but these do pop up every once in a while. So the first one, cosine 2x, on your sheet, how did you write cosine of 2x? Start with
Cosine
2x.
x cosine.
Yeah. We've already proven the composite argument properties, so that's what we're using here. And then cosine of x plus x, we could rewrite as cosine x minus sine x sine x. And then because the arguments are the same in both cases, you can write cosine x as cosine squared x. And then sine x as sine squared x. So this is one way that you will see the double argument property for cosine. The double argument property for sine, or one version of it, actually comes from something we've already proven, which is this guy here, because you notice that you have a double argument right there, sine 2x, and we already proved that on the first page, so I'm not going to make you reprove it here. But it's just a reworking of that property. And all they do here, since we've already proven it's true, now you can start moving stuff from side to side. They just get rid of that fraction by multiplying by 2. So they say, okay, if I multiply both sides by 2, then sine 2x is going to equal 2 sine x cosine x. So if you look at your property sheet, does anybody have it out so I can throw at it real quick? So we've gone through all of these. Not that you can see. We've gone through and proven most of these composite argument properties, which means you're allowed to use them anytime now that we've proven them. We've actually proven all of these at this point. Double argument properties are the ones now that we're looking at. You can see that sine 2x is this expression 2 sine x cosine x. And then cosine 2x, this is one way to write it. But as you saw in your sheet, you could always replace cosine squared with 1 minus sine squared. So you could write it like that. Or you could replace sine squared with 1 minus cosine squared and write it like that. So the cosine 2x is the most versatile because there's 3 different ways that you can write it. So that's actually the one we use the most. And then you see tangent 2x. There, we're not going to prove that one. It's proven very much like the other ones were proven with tangent, where you rewrite it in terms of sine and cosine. And then these two are the other ones that we've already talked about. Now, they are written a little bit differently than on your sheet. What did they do here? Like with sine squared, what did they do between the two? They didn't multiply by 2.
Half. They took out a half.
They took out a half. All they did was factor out a 1/2 on your property sheet, but it's essentially the same exact thing. So now, through this sheet that we've just done, we can use any of those double argument properties. Now these properties are going to be used a lot of times just for solving equations. For example, 1 is actually what we're going to use it for. You can also use it to find exact values for shapes with triangles like we've done for the other ones as well. So let me look at the time really quick and then I might do an example. Or not. I think it's where we'll end today. Tomorrow we're going to finish this out. And just so you know, my plan is to finish out this note packet this week. And then Monday, Tuesday, and Wednesday of next week we review the ORP. And then I'm having you take your test on that Wednesday before Thanksgiving, so you don't have anything to do on Thanksgiving break.
Sweet.
Okay?
Give the ORP on my
I can. I'm going to write a more detailed rubric too for it. I'm doing that tonight. Hopefully help everybody feel like they can be as